Good evening, Year 11, and welcome to your night before physics revision. What we should be looking at this evening are the two required practicals from the electricity topic, the resistance of a wire and the IV characteristics, and also a quick recap of the rules in series and parallel circuits regarding current, potential difference, and resistance. So, starting with the resistance of a wire practical. This one could ask you questions about the experimental setup, including a 6-mark long answer question about how to set the experiment up. You could be asked to analyze results. You could be asked to draw a graph. You could be asked to explain the results that you are given. So the circuit is set up, as you can see in the diagram here. There is a power supply with a switch usually. There is an ammeter for recording the current. There is a voltmeter for recording the potential difference. And the piece of wire that you are testing is connected to a 1-meter ruler, and the connections to it are made with crocodile clips. One is fixed and the other one is movable. From a safety point of view, the maximum power supply voltage should be set at no more than 4 volts. This prevents the current from being too large, which could cause the wire to overheat. Also, if the current is switched on, then it is advisable to not touch the wire, as there is no insulation and you could burn your fingers. When it comes to writing a method for this, some key points that you must include: the ammeter must be connected in series so that the current can flow through it. The voltmeter must be connected in parallel to the wire so that it can measure the potential difference across it. One end of the wire is connected at the 0 end and the other end is movable so that you can test different lengths of wire. So we have our circuit set up like that. The independent variable in this experiment is thus the length of the wire. So starting at a 10 centimeter length and going up in 10 centimeter increments up to a maximum of 100 centimeters will give you a sufficient range of readings. The switch is there so that you can switch the circuit on for just long enough that you can record the readings on the ammeter and the voltmeter without actually causing the wire to overheat. It's really important that you switch the circuit off before repositioning the crocodile clip to change the length of the wire, as the wire will still be hot when the electricity is running through it and we wouldn't want you to get burnt. Moving on, the dependent variable in this case is going to be the resistance of the wire. So once you have calculated the resistance using Ohm's law, the resistance is equal to the potential difference divided by the current, both of those readings from your meters. You can then calculate the resistance of the piece of wire. You may be asked in the exam question about repeating so that you can calculate an average. You may also be asked about repeating the experiment for a wire of different thickness so you can compare the effect of cross-sectional area of the wire on its resistance. So once you've completed the table of results, you can then plot a graph of length against resistance. And in this case, you should find you get a graph that looks like this. It is a straight line that starts at the origin and goes diagonally up to the right. Now, importantly, on this one, you must make sure that the independent variable is on the horizontal axis. In this case, it's length of wire with its units. The dependent variable goes on the vertical axis. That will be the resistance. And as you can see here, you'll get a straight line graph that goes through the origin. The key phrase they're looking for here in exam questions is for you to say that the resistance of the wire is directly proportional to the length of the wire. Any straight line graph that goes through the origin, key phrase is directly proportional. If you said as the length increases, the resistance increases, that would only get you partial credit. That 2-word phrase there, directly proportional, is the important one. If you've been asked to compare wires of different thickness, different cross-sectional areas, and you plot both sets of data on the same axes, you will find that you get two lines like this. Both are straight lines, both are through the origin, so both are directly proportional, but the thinner wire will have a steeper gradient, and that's because the thin wire has a much higher resistance per unit length than the thick wire does. The thicker wire, being wider, has more pathways for the charge to flow through it, and so the resistance of a thick wire is always lower than the resistance of a thin wire for any length of wire. The second required practical on the electricity topic is the IV characteristics required practical, the current voltage characteristics. For this experiment, there are three components that you're asked to test. They are the fixed resistor, the filament lamp bulb, and the diode. The circuit setup is very similar, and again, you could be asked to draw a circuit diagram. So for the fixed resistor and for the filament lamp, the same circuit is used. There is an ammeter to measure the current, which must be connected in series with the component you're testing. There is a voltmeter that is connected in parallel. The variable resistor is there to control and vary the current in the circuit so that you can collect results. When you do the same experiment for the diode, there is an additional resistor connected into the circuit as part of the circuit, still connected in series. That reduces the current even further because the diode is very sensitive to large currents and could easily be damaged. You may see this symbol being used for the ammeter. That means it's a milliammeter. That means it can read much smaller values of current than a standard ammeter. But if you see the standard ammeter symbol, it's the same thing. It's not going to cause you any problems. Now, coming back to the resistor. When you've got the circuit set up like this, you want to collect between 5 and 8 readings with the voltage and the current going in the forward direction. So both of your meters should have positive readings on them. Once you've collected those readings, you then disconnect the power supply, disconnect the battery, and swap the connections round. This will cause the current to go through the circuit in the other direction, and that will cause the readings on the voltmeter and the ammeter to become negative. You will then have two sets of readings, one in the positive direction and one in the negative direction. You repeat this process for the filament lamp again, and you repeat this process for the diode. When you do the diode, just ensure that the voltmeter is only connected across the diode and not the additional resistor as well. From here, you would then be plotting graphs of these results, and you could be asked to identify components based on those graphs. The graph for the fixed resistor looks like this. It is a straight line that goes through the origin. That tells you the relationship between current and voltage is directly proportional. You'll also notice that it works when both values are negative. This means the fixed resistor will work regardless of the direction of current flow through it. The gradient of that line can be used to calculate the resistance of the resistor. One little caveat on this particular experiment is that this only is true if the resistor is kept at a constant temperature. If the resistor gets too hot, its resistance may change. The graph for the filament lamp looks like this. It starts off following a straight line, but very rapidly that line curves. The reason for that is that as the voltage increases, the filament lamp actually increases very rapidly in temperature, and as it increases in temperature, its resistance increases, and therefore you get less current for the same amount of increase in potential difference. The positive direction and the negative direction are both shown. Again, like the resistor, the lamp works in both directions. The upper right section should be a complete mirror image of the lower left section. So if you're given half the graph, you have to plot this, and you have to plot the second half, it needs to match in terms of its shape. The final component is the diode. When you plot the graph for the diode, you will discover that regardless of the potential difference in the negative direction, there is no current flow through the diode. The diode is a type of component that only works when the current is going in the forward or positive direction. However, there is also a minimum potential difference that is needed before current starts to flow. That minimum potential difference is called the threshold voltage, and it's usually around about 0.7 volts, as you can see from the graph here. And then the current will rapidly increase with a very small increase in potential difference. You cannot describe this relationship as directly proportional because it doesn't go through the origin. So, as I mentioned a little while ago, those three graphs show very different current voltage characteristics. You could get a question where you're presented with that graph and asked to identify the component. Sometimes they're multiple choice, sometimes they are matching questions, sometimes you could be asked to sketch them. And finally tonight, a quick recap of the rules for current resistance and potential difference in series and parallel circuits. So we'll start with series circuits, and the first rule is the rule for current. The current in a series circuit is the same everywhere. It doesn't matter where you position the ammeter. There are two positions shown on the diagram here. Equally, it could be positioned between the resistors. It doesn't matter. Wherever you put it, the current will be the same. There is only one pathway for charge to flow around a series circuit, and it's all moving at the same rate. So wherever you put the ammeter, the current will be the same. The rule for resistance, however, in a series circuit is that the resistance increases with the more components you add. So each component has its own resistance. By adding more components in series, you increase the total resistance in the circuit, and as a result of that, the current will go down. So here you can see two resistors, the current is 0.5 amps. If I add a third resistor in there, you'll see the current decreases to 0.3 amps. The rule for resistance in a series circuit is this. The total resistance is equal to the sum of the individual resistances. So the total resistance equals the resistance of resistor 1 plus resistor 2 plus resistor 3. Potential difference is measured using voltmeters. The voltmeters must be connected in parallel with the components you are testing. There is always one that is connected across the power supply. That will tell you the voltage being provided by the power supply. And then other voltmeters are connected across the components to be tested. So in this example, the power supply is providing a potential difference of 6 volts. That 6 volts will be shared between the components. Now, if they are identical, and a question will clearly state whether components are identical or not, the potential difference is shared equally between them. If they are not identical, it will still be shared, but not equally. So the rule for potential difference in a series circuit is that V across the power supply is equal to the voltage across component 1 plus the voltage across component 2. That rule applies regardless of the components. For example, here you can see the components are not identical. One has, in this case, a much higher resistance. The rule still applies, but the component with the highest resistance has the larger share of the voltage. More of the energy is being used up by that component, so the potential difference across it is greater. Moving on to parallel circuits. Parallel circuits are slightly different. In a parallel circuit, there is more than one pathway for the charge to flow around the circuit, and so the current splits between the different branches on the circuit. The ammeter at the top will give you the total current in the circuit because all of the pathways include that part of the circuit, but an ammeter placed on any one of the individual branches will just give you the current flowing through that branch. The total current is therefore the sum of the individual currents in the individual branches. If the components are identical, that current will be shared equally. If not, then the component with the highest resistance gets the least amount of current, and the component with the lowest resistance will get more. For resistance in parallel circuits, the total resistance of resistors connected in parallel is always less than their individual resistances. If you're doing foundation tier, that's the key point that you need to know. Resistors connected in parallel, the total resistance is always less than the individual resistance. In the case of identical components connected in parallel, the resistance for two resistors connected in parallel is equal to half the value of one of them. For three resistors connected in parallel, it's 1/3 of the resistance of one of them. And as you add more components into the circuit, the resistance will continue to get lower and lower and lower. It will always be lower than the smallest individual resistance in the circuit. And finally, the rules for potential difference in parallel circuits. Unlike the series circuit, where the potential difference is shared, in a parallel circuit, each branch of the parallel circuit receives the full potential difference being supplied by the power supply. So V power supply equals voltage across component 1, which is equal to voltage across component number 2. It doesn't matter if the components are identical or not. If they are the only component on the branch, they receive the full potential difference as supplied by the power supply. And that will leave it there for tonight. Good luck with your exams tomorrow.